Hello, students. We're going to look a little bit at some of the rules for compound probability. These first couple of examples use a case where you're looking at the probability of one thing or another. And in those cases, you can take the probability of the first and add the probability of the second, but it kind of depends. If you have two things that are mutually exclusive that cannot both happen at the same time, then you can take the probability of one and add the probability of the second. In this case, in this particular problem, that isn't the case. These are not mutually exclusive events. We can tell it because we have the probability of A is the probability a customer orders pizza. Probability B is the probability a customer orders a salad. And the probability of A and B is the probability they order a pizza and a salad. And that's not a zero. There are customers who order both. In fact, there are 8 of them. So both things can happen at the same time and sometimes do. So we have of 22 customers eating dinner at an Italian restaurant, 18 ordered pizza, 10 order a salad, 8 order both pizza and a salad. So let A be the event that they order pizza, let B be the event that they order a salad. What's the probability of A? Probability that a customer orders pizza. Well, there are 18 orders for pizza out of 22 customers, so they're 18 out of 22. 8 over 22, or 9 over 11, which would be about 81%, 82%. The next question is, what's the probability of B, the probability that the customer orders a salad? There aren't as many of them. There are only 10 who order salad. So the probability would be 10 out of 22, or 5 out of 11. So that probability is about 45%, 45.5%. Now, those are both simple probabilities. There's no compounding there. Now, we're not saying what's the probability of this and that, or the probability of this or that. This next question is, what is the probability of A and B? The probability that the customer ordered a pizza and a salad. Well, if you look at the Venn diagram, here we have A. Those are all the people who ordered pizza, and there are 18 of those. Of those, there are 8 who also ordered salad. Well, if we take that into account, then we can say, well, there are 8 who did that. There are 2 more who ordered salad, which would be in B. And go back the other way. There are 18 who ordered pizza. 8 of them ordered salad as well. So there are 10 who ordered just pizza. So we can see that in this kind of half moon here, we have 10 people who ordered pizza but not salad. 8 more who ordered both. 2 who ordered just the salad. Probability of A and B that they ordered both? Well, those would be the 8 who ordered both. So 8 out of 22, which would be 4 out of 11, or about 36%. What's the probability of A or B? The probability that a customer ordered a pizza or a salad. Well, this gets a little trickier. That means everything that's in A, everything that's in B. But if we take everything in A and everything in B, so 18 and another 10 would be 28. We can't have 28 out of 22. That doesn't make any sense. Well, that's because we're double counting the 8 that's in the middle here. So we actually have 10 who ordered just pizza, 8 who ordered both, 2 who ordered just salad, or a total of 20 people. So 20 out of 22 would be the probability. 20 out of 22, or 10 out of 11, which would be 91%. So 91% would be people who ordered either pizza or a salad, or both. Hero rolls a fair pair of 6-sided dice. The sample space of all possible outcomes is shown below. Let A be the event that the first die is 1, and B the event that the sum of the dice is 8. Well, for the first part of this, we can look at just the first column here. The probability that the first die is 1. That's everything over here, where they rolled 2 ones, or 1 and a 2, 1 and a 3. So there are 1, 2, 3, 4, 5, 6 different ways in which they could have rolled a 1 first. So 6 out of a total of 36, or 1/6 of the time. For the second part of it, the sum of the dice is 8. Well, there are 1, 2, 3, 4, 5 cases where you could roll a sum of 8. Now notice none of these include rolling a 1, because to get 8 that way you'd have to roll a 1 and a 7, and you can't roll a 7 on a 6-sided die. So these are what are called mutually exclusive events. They cannot both happen. You can't both roll a 1 on the first die and roll a sum of 8 altogether. So we can just add these two probabilities. We have 6 out of 36 here. We have 5 out of 36 here. So we have a total of 11 out of 36, which would be about 31%. Now, if any of these had fallen over here, so if we had had a sum of 7 instead, then we'd include 1 and 6, and we'd have to discount that or subtract it out when we added in our sums of 7. Okay, but in this case, they're mutually exclusive events. We just find one probability and add the second probability. So 6 out of 36 plus 5 out of 36 is 11 out of 36, or 31%. When you have independent events, you can find the probability of one and multiply it by the probability of the other. Captain Kevin has a ship, the HMS Khan. The ship is 2 furlongs from the dread pirate Ben and his merciless band of thieves. The captain has a probability of 3/5 of hitting the pirate ship. The pirate only has one good eye, so he hits the captain's ship with a probability of 1/5. If both fire their cannons at the same time, what is the probability that the captain hits the pirate ship, but the pirate misses? Well, the probability of the pirate hitting the ship is 1/5. Probability of him missing the ship would be 4/5. So the probability of one thing and another means you can multiply these two probabilities if they're independent. The chances of the captain hitting the pirate ship, the pirate hitting the captain's ship, are independent because whether they get hit or not, they're shooting it at the same time. They will not affect each other. So we would take those two probabilities, 3/5 times 4/5, and we get 12 25ths. So I'm going to put that in as 12 divided by 25. And that's right. If you flip a coin and you roll a 6-sided die, what's the probability that you flip it tails and roll more than a 3? Well, those are independent events. It doesn't matter what you get on the coin. It's not going to affect what you get on the die. That makes them independent. Chances of flipping a coin and getting tails is 1/2. Probability that you roll something more than a 3, well, that means it could be a 4, 5, or 6. That's 3 out of 6, or 1/2. So you've got a 1/2 chance of getting tails. You have a 1/2 chance of rolling something more than 3. So 1/2 times 1/2, 1/4, or 0.25 if you want to put it in as a decimal. This one is a bit more complicated. Kobe Bryant is shooting free throws. Now, making or missing free throws doesn't change the probability that he'll make his next one. And he makes his free throws 83% of the time. What's the probability of Kobe Bryant making all of his next 6 free throw attempts? Well, the probability of the first one is 0.83. Probability of the second time, 0.83. Probability of the third time, 0.83. So each of these 6 times is going to be 0.83. It's not changing. So you multiply those, 0.83 times 0.83 times 0.83 6 times, which is the same thing as saying 0.83 to the 6th power, which is correct. You've decided you want a plant for your room. At the gardening store, there are 4 different kinds of plants: tulips, ferns, cactus, and ficus, and 8 four different types of pots. So if you randomly pick the plant and the pot, what's the probability that you'll end up with a tulip and a plastic pot? Well, the chances of picking a tulip randomly would be 1 out of 4. The probability of picking a plastic pot would be 1 out of 4. Now, these seem to be independent events. Apparently, you can get any plant in any type of pot. So we would multiply 1/4 times 1/4, and we should get 1 out of 16, which is correct. Now, these are dependent events. The bag contains 6 red jelly beans, 4 green jelly beans, and 4 blue jelly beans. So there are 14 beans altogether. If we choose a jelly bean, then another jelly bean without putting the first one back, because that would be gross. What is the probability that the first jelly bean will be green and the second one will be red? Well, the first one, there are 4 green jelly beans. They're a total of 14. So 4 out of 14, or 2 out of 7. For the second one, now we've taken one of these jelly beans out. There's one less green jelly bean in the bag. So what's the probability that the second one will be red? Well, there's still 6 red jelly beans, so 6, but now it's out of 13. So 6 out of 13. And if we multiply those together, we would get 12 out of 91. And if we do that as a decimal, we get about 13.2%. So I'm going to try putting it in that way. It's 13.2. They may not like the decimal. They didn't quite like it. We're going to move on. In a class of 10, there are 5 students who play soccer. So if the student chooses 2 students, what's the probability that both of them play soccer? Okay, so for the first student, there are 5 out of 10, or 1/2. For the second student, now we've already taken out one of the students who play soccer, so there are 4 of them left. There are 9 students left, so the probability would be 4 out of 9. And if we multiply those, we're going to get 4 out of 18. Let's try putting it as a fraction, see if they like that. That worked. So when you have dependent events, you have to look at the first one is pretty straightforward, but the second one, you have to determine how it depends on the first. What changes? The total is bound to be down by 1, but it may be that the thing you're trying to find is also down by 1. So be careful with these. Make sure you come up with that second probability, which is known as a conditional probability because it's based on a condition of whether the first one was successful. Okay, good luck with these.